Okay, let's look at Young's double slit in a little more detail. So we said that we need a screen that has two holes in it. Okay, there's our double slit. And then we have a viewing screen. Alright, if I think about a region on the screen here, right there, light from this slit has to travel a distance L1 to get to that point. Light from this slit has to travel a distance L2 to get to that point. And let's say this point is halfway in between. If it's halfway in between, then L2 is in fact equal to L1. So the wave I get from the first slit maybe looks like that. The wave I get from the second slit will look exactly the same. And so the result is a nice big field there, lots of light. But now let's do the experiment again, and let's look at a different point on the screen. Okay, so here is our slits again. Here is our screen. And let's look at a point that is maybe up here a little bit higher. Alright, that travels some distance. We can still call it L1 for now. Let's say that this light travels a farther distance, L2, and in this case, let's let L2 be a half a wavelength longer than L1. You kind of probably know what's going to happen, right? The field from L1 looks like that. The field from L2 is going to be the exact same thing, except it's going to be shifted over by a half a wavelength. If I shift a wave by a half a wavelength, that's really the same as flipping it over. So it's going to look like this. And now look what happens. We've got positive here, negative there. That's going to add up to 0, and in fact it's going to be 0 everywhere. This was lots of light, constructive interference. This is no light, destructive interference. Since light from slit 1 goes everywhere and light from slit 2 goes everywhere, the entire screen is illuminated, and so you can look at this relationship anywhere up and down the screen to calculate what's going to be a maximum, what's going to be a minimum. Maximum is what we call constructive interference. Minimum is destructive interference. Okay, let's extend this argument a little further. Let's say we have our double slits and our view screen. We've already looked at the center point. We looked up a little bit, but let's look up even farther. So let's say we go from this point right here. If this is L2, and L2 is now a full wavelength longer than L1, then what happens? L1 gives us a field that looks like that. L2 gives us a field that looks like that, but shifted over by one wavelength, which means it looks exactly the same. That's what happens when you shift a field by one wavelength. So again, we're back to the constructive case. We have maximum intensity of the light at that point. So you kind of see what's going on here. We had a maximum, then we went to a minimum, then we went back to a maximum. And indeed, if you think about where the maxima are, anytime you add another wavelength of distance to L2, you're going to get a maxima. And so there's a nice little equation that we can write down. L2 is equal to L1 plus m times lambda. That's where all the maxima are on the screen. All the minima, namely those dark spots, are going to be at L2 equals L1 plus, remember, a half a lambda got us a minimum, but we could add another wavelength to that half a lambda and we would still get a minimum. So what we need here is in fact m plus a half lambda. This is where all the maxima are. This is where all the minima are. All right, let's redraw this again and we'll look at a screen that's far away. Okay, so with the double slit interference, let's draw it again and let's put our screen rather far away. So here are the slits, and now we will put the screen farther away. And now let's think about the light that propagates from slit 1, takes a distance L1, and the light that propagates from L2 takes a distance L2. If I draw a perpendicular to L2 from slit 1, then I can identify an angle here, theta. And that angle theta turns out to be about the same as this angle theta. Okay, if the screen is far away, then the distance from the center of the slits to the screen is pretty long, and if I make that angle, it's roughly equivalent to that angle there, theta. Well, let's mark the distance d between the slits, and let's also mark this little distance right here as delta L. Alright, so what is delta L? Delta L is just the difference between those two paths, L2 minus L1. Okay, it's this little distance right here. But we can also use a little geometry with this triangle right here, a little trig, I guess. This triangle, this triangle has a right angle in it, that angle right there. And so we can write delta L in terms of d and the angle, and sine of theta is delta L over d. So delta L is equal to d sine theta. Okay, let's look at our condition for maxima. What we said was for maxima we have L2 minus L1 equals L1 plus m lambda. That's what we had for L2. We're going to subtract the distance L1. So the L1s drop out and we just get m times lambda remaining. So what's the equation for maxima? It is this thing, which is this thing, which is d sine theta. D sine theta equals all of this stuff, m lambda. Okay, if you want to know where your maxima lie in terms of angle, this is the equation that tells you exactly where they are. Now, you can do the same thing for minima. The only difference is in the substitution right here, you would add L1 plus m plus a half lambda. Okay, so you can try that for yourself. It's fairly straightforward, but what you end up with is an equation for the minima, which is the following: d sine theta equals m plus 1/2 times lambda. Okay, those are our two equations. One equation that tells you where the maxima are, a second equation that tells you where the minima are.